lecture 24, part 2. In this lecture, I want to finish talking about ordinary differential equations, and then I want to give you some physical interpretations of what we learned about second-order systems, namely, what is the meaning of complex and real roots of the characteristic equation. So the first thing I want to do is I want to talk about the method of, okay, so what have we learned so far? So far in Professor Lott's lecture and in Professor Paulin's lecture, we learned how to solve the initial value problem for a homogeneous system, x prime equals ax, where we found that the fundamental solution set was given by eigenvalues and eigenvectors of A. So we figured out how to find this when A was diagonalizable with real or complex eigenvalues. So we're not going to discuss the non-diagonalizable case. So we're going to skip the case of non-diagonalizable A, which is in section 9.8, and it's optional if you are curious. But what we're going to do now is talk about how to solve the inhomogeneous system. X prime equals ax plus f, where f is now, so remember, what are the types of these objects? Well, these are vector valued functions. So I'm going to put lines under everything. So remember that this x is a function from R to Rn. So it's something, you can think of that as a function where x of t is a vector, or x of t is itself, it's a vector whose entries are univariate functions. Okay, so A is an n by n matrix, and f is, so x is the thing, it's an unknown function, and f is a fixed function from R to Rn that we're given as part of the problem. And the question is to find an x satisfying this equation for a given f. So as before, what we're going to do is we will only solve for, we'll only discuss how to solve this problem for special cases of f, namely just the case when f is, when the entries of f are polynomials. So this is in p to the n. Remember, p is polynomials in T. And we're going to do this using the method of undetermined coefficients. Okay, so rather than give you a theorem explaining the method of undetermined coefficients, I'm just going to show you one example to make it clear how to do this. And the idea is the same as in the second order case. So let's look at an example. Let's look at the system x prime equals some matrix, which is the matrix 1, 3, 0, 2 times x plus the function t square, whose entries are t squared and t. Okay, so this is the function f. This is the matrix A. And the question is, you want to find a function x from R to R2 which satisfies this equation. So how would you do this? Again, the idea is, well, okay, we're looking for this x so that when you differentiate it, it's equal to itself times some matrix plus a vector of polynomials. So what are the functions, what functions do you get when, which functions differentiate to polynomials? Well, polynomials. So the idea is to look for solution X restricted to a specific subspace of functions, polynomials, um, well, P superscript 2 is vectors whose entries are vectors of two in 2 dimensions whose entries are polynomials. We probably don't want polynomials of arbitrary degree because remember this is a quadratic polynomial. The degree is equal to 2. And as we saw in the case of second order differential equations, to solve an inhomogeneous equation with a inhomogeneous term is a polynomial of degree 2, you just need polynomials of degree 2. So we're going to make the same guess here. We're going to look for x being a polynomial of being a vector of polynomials of degree 2. In other words, x of t should look like, it should be a vector with entries c0 plus c1t plus c2 squared. That's the first entry. And the second entry is, let's say, as coefficient c0 prime plus c1 prime t plus c2 prime. So we're going to look for solutions of the specific type. And the point is that this is a finite dimensional subspace, right? So, so we can use standard finite dimensional linear algebra to solve this. So, so what we're going to do is we're going to write this slightly differently. Right now, I've written it as a vector, each of whose entries is a polynomial. But I could also just, group it by the terms, the constant terms, the t terms, and the t squared terms, and write this as c0, where c0 is a vector, plus c1, where c1 is a vector in R2 times t, plus c2, where c2 is a vector in R2 times t squared. And now my goal is to find these vectors c0, c1, and c2. Right? So what's the relationship? So c0 is a vector with coefficients c0, c0 prime. C1 is a vector with coefficient C1, C1 prime, and C2 is a vector with coefficient C2, C2 prime. These are vectors in R. My goal is to find these vectors in a way that satisfies this inhomogeneous equation. Okay, so let's just write down what's happening. So the left-hand side of the equation is what you get when you differentiate x. So that's just going to be d by dt of this c0 plus c1t plus c2t squared, which is, so the constant term goes away, the linear term just becomes c1. So you get this. Now what about the right hand side? Well, the right hand side is going to be ax of t plus this f of t. And so that's going to be a c0 plus a c1t plus a c2t squared plus f. And now again, I'm going to write f slightly differently. F was given as a vector of polynomials. I'm going to write it as a polynomial whose coefficients are vectors. So f is just going to be the vector 0, 1 times t plus the vector 1, 0 times t squared. Okay, so I've written both the left-hand side and the right-hand side as polynomials whose coefficients are vectors. Okay, but now the left-hand side must be equal to the right-hand side, so these must be equal. And what that means is that the coefficient, the constant term on both sides has to be equal. So C1 has to equal AC0. Similarly, the coefficient of t on both sides has to be equal. So this 2c2 term has to equal the coefficient of t, which is actually a sum of two things. And the coefficient of t squared, which in the bottom is the vector 1, 0, has to equal the coefficient of t squared here, which is 0, 0 vector, right? So actually, this equation of polynomials, but now polynomials with vector coefficients, by comparing terms, gets me three equations which equate the coefficients of 1, t, and t squared on both sides. So now let me write down these equations and solve them. Okay, so what are the equations that we got? So let's write them from highest degree to lowest degree. So we got a c2 plus 1, 0 equals 0. Then we had 2c2 equals ac1 plus 0, 1. And then we had ac0 equals c1. So this might look a little bit unfamiliar to you. It's the unknowns are these three vectors, c0, c1, and c2, and there are three equations. So it actually looks like a system of linear equations in these vectors, which looks like a new type of object from what we've seen before. But actually, you can solve this using row reduction in stages uh, if you do it in the right order. So the first thing to observe is the top system here. This is actually just uh, a linear system in one variable, namely C2. And so you can actually solve this. Um, uh, you can just solve this using row reduction. So C2 should be equal to A inverse, or well, C2 should be the solution to the system 1, 3, 0, 2 minus 1, 0. So maybe equals is the wrong thing to say here. It's a solution to this linear system because I can move the 1, 0 to the other side. And if you row reduce this, you actually just get the vector minus 1, 0. Okay. And the reason this had a solution is because A was invertible, and we're always going to assume A is invertible in the in the problems that you get here. I'm not going to give you a not invertible A. Okay, but now this is good because I can plug this in to the second equation. So the second equation originally had two unknown vectors, but now I found out what C2 is, right? So now I go to the second equation. The second equation becomes AC1 equals 2C2, but 2C2 is just this vector minus 1, 0, minus 0, 1. And again, that's just a linear system that I can solve. And I can, I'm not going to do the row reduction, but I can do this to get C1, right? And once I get C1, I plug this into here. And now this becomes a linear system just in C0, right? So this is linear system in C1, this is linear system in C2. The last one is linear system in C0 because I know C1 from my previous approach. When I plug this in, I can solve to get C0. So finally, I got C0, C1, and C2. So finally, I get a particular solution, xp, which is equal to C0 plus C1t plus C2t squared, with the C0, C1, and C2 being, whatever I got up here. So I have to do row reduction 3 times, okay? It's quite painstaking. But each time I did it, I learned a new coefficient of this particular solution. Okay, so I want to emphasize this is a particular solution. Just as in the second order case, when you have an inhomogeneous system, you have that the general, or you have the set of all solutions to the inhomogeneous system, which is x prime equals ax plus f. The set is equal to the set of solutions to the homogeneous part, which is what you get if f is 0, plus any particular solution of the inhomogeneous part. So that's the thing we just computed. And so in particular, what that means is that the general solution to this equation is actually x of p equals this thing that I computed above, the particular solution, okay, plus whatever I get from solving the inhomogeneous system, which I already know how to do. So so in this case, it's an upper triangular matrix. So the eigenvalues are just 1 and 2. So I know, and the eigenvectors are, something I haven't computed, but I know that the general solution is going to look like C1 e to the t u1 plus C2 e to the 2t u2. Okay, this matrix is definitely diagonalizable because its eigenvalues are 1 and 2, which are distinct. So that's how you find the general solution. Okay. So in this course, you're not required to know how to do undetermined coefficients for systems of equations for anything other than polynomials. Okay, the only thing I'm going to ask you to do is polynomials. Okay, so now what I want to do, so in the last, 3 or 4 lectures, we've learned a lot of stuff, and it might seem like we're just learning a lot of random facts that are not related. So what I want to do is summarize everything in one slide to make it clear that there's like actually a very clear pattern. So we've done two things. On one hand, we've learned how to solve the initial value problem for second order systems. So that's a system, for second order differential equations. That's an equation like ay prime plus by, sorry, that's b plus cy equals f, subject to some initial data that pi at 0 is equal to some y naught, y prime is equal to y1. And we're looking for a function y that's in this vector space that I called capital F, which is functions from R to R that are infinitely differentiable. Okay, so that's a vector space. And there were 3 steps to doing this. So the first step, so it's an inhomogeneous system. The first step was to solve the homogeneous part, which is just what you get if you throw away the right hand side. So a at y double prime plus by plus by prime plus cy equals 0. And this, when you solve this, you get a basis of solutions, a two-dimensional subspace of solutions that we called y1 of p and y2 of p. And these were both, again, viewed as vectors in the subspace. And what was the method? Well, the method was to look at the auxiliary equation, where you turn these derivatives into r's, and you get some polynomial, and you find its roots, and use that to factor the operator, and you get these solutions that are exponentials. Okay. The second step was, what do you do when it is inhomogeneous? So if f not equal to 0, find some particular solution. Um, just find one to the inhomogeneous equation. And the method here was a method of undetermined coefficients. Okay, so this is this thing where you said, well, I'm going to look at f, if it looks like, a polynomial or an exponential, then I can guess that the thing that it came from also looks like that, and I'm just going to look in that subspace. And then the third step was fitting what you got to the initial data. So the first two steps gave you a general solution. It gave you a two-dimensional, well, okay, not subspace, but a translation of a subspace of functions which solve this equation. And the third step, you want to find one that fits the data. And so to do that, you have to solve a linear system which always looks like this. So you're looking for these coefficients in the general solution. And that has to equal your initial data. But if it's inhomogeneous, then you, of course, also have to evaluate your particular solution at the initial point 0. But now this is just a 2 by 2 row reduction problem. The reason this is always solvable is, well, it's row reduction, but the reason it's solvable is that there's this Wronskian lemma, which tells us that this is always invertible. Okay, so that's a summary of the workflow for solving a system of second-order differential equations. Now let's compare this to what it is for solving a system of first-order ODE, which looks like x prime equals ax plus f, possibly with some initial condition that at 0 the vector is equal to some fixed vector x naught. So again, this had 3 steps. And again, I should say this time the one difference is we're not looking for a real valued function, we're looking for a vector valued function. So let me call this vector space capital F to the n. This is the space of all functions from R to Rn. Okay, so that's one difference. Previously we were looking for a scalar valued function, now we're looking for a vector valued function. But actually at a high level the steps are exactly the same. So the first step is to solve the homogeneous part, which is x prime equals ax. And when you do this, you get a basis of solutions, but of n solutions, which let's call them x1 through xn. So okay, so these are, again, I'm putting an underscore here because these are vectors. These are not the entries of the function x. And these, ended up coming from eigenvalues and eigenvectors of the matrix in the system. And maybe you had to do a little bit more work when they were complex, but the method was basically diagonalization. Okay. And so this looks like it's a little bit different. I mean, this looks like it's different from the auxiliary equation. But actually, if you think about diagonalization, well, how do you find eigenvalues? You compute a characteristic polynomial, and you find its roots. You might wonder, is there any connection between these two things? And actually, I'm going to show you the next slide. These are actually just, I mean, these are the same thing. So what we did for second order systems can be seen as a special case of this diagonalization procedure by the reduction from second order to first order, and I'll show you that in the next slide. So it's actually not fundamentally different. And okay, we only discussed how to do this for diagonalizable matrices, and that's all we'll discuss. The second step we only applies again if it's inhomogeneous. So if f not equal to 0, find a particular solution. Again, using the method of undetermined coefficients only for polynomials. Okay, so but same high level idea, same idea of zooming in on a subspace and looking for a solution in that subspace. And then the third step, I have to fit my general solution to a specific solution. And now instead of a 2 by 2 linear system, I get an n by n linear system. So I get x1 of 0. I'm trying to find a linear combination of my fundamental solution set, my vectors in my fundamental solution set. So the linear combination looks like this. It has n coefficients, and this should be equal to whatever my initial data is, minus my particular, I'm sorry, not y, this is x, minus my particular solution at 0. And again, the method here is row reduction, but the reason it works is because of the Wronskian, this lemma that says that whenever you have a bunch of solutions to a linear system, to a system of differential equations, they're linearly independent as functions if and only if these vectors that you get when you evaluate them at 0 are linearly independent as vectors in Rn. Okay, so you see the similarity. It's actually identical. You don't have to. It's the same process at a high level. The details a little bit different. Okay, so now I want to explain, what's the connection between between the method we use to solve second order system, homogeneous second order system, and I don't know what symbol to use here, and which was this auxiliary polynomial, and the method we used to solve a homogeneous system of ODE, which was a diagonalization method, right? So here we had an auxiliary polynomial, and here we had the method of diagonalization. Well, okay, so what's the auxiliary polynomial for this system? Well, it's AR squared plus BR plus C, right? Okay. But now, suppose I didn't know about the auxiliary polynomial. Suppose I wanted to reduce the second order system to a system of two, the second order equation to a system of two first order. So Professor Lott showed you how to do that. How do I do that? Well, I introduced this new variable. So let's say x1 equals y. Now introduce a new variable x2 to be y prime, which is just x1 prime, right? So when I introduce these variables, my equation, I get a system of equations. So one equation is just this, that x1 prime equals x2. And the other one is, if I rewrite my second order equation in this way, it becomes ax2 prime. So the y double prime becomes x2 prime plus bx1. So remember I'm sorry, not bx1 plus bx2. x2 is just y prime plus cx1 equals 0. Okay, so now I have these two first order differential equations, and I can write them in this normal form I can write them as x1 prime equals x2 and x2 prime equals minus b over a, or let me write it in order, minus c over a x1 minus b over a x2, right? That's just the second equation rearranged slightly. But now I can write these in matrix form. So in matrix form, this is just x prime equals ax, where x is now this two-dimensional vector valued function, where A is the matrix, well, given by these two equations. So A is going to be the matrix 0, 1, and minus C over A minus B over A. And now, in order to diagonalize this, I need to find the characteristic polynomial of this matrix. And you can guess what's the characteristic polynomial of this matrix. So let's compute it. And let's suggestively put in the variable r. So this is going to be determinant of minus r, 1 minus c over a minus b over a minus r. And if you calculate that, you get that it's r times b over a plus r plus c over a, which is just, if you expand it out, this is just r squared plus b over a r plus c over a, which is actually the same thing as this polynomial, just scaled by a. And that's what I meant when I said they're the same. That you could reduce the second order system to the second order equation to a system of two first order equations, compute the eigenvalues. The eigenvalues would just be the roots of the auxiliary polynomial. So actually, these are two different ways of doing the same thing. The reason we studied them separately is that I wanted to do the second order equation in full detail. Because remember, for the system of ODE, we only did the diagonalizable case. We didn't do it in full detail. But I wanted to do the second order case in full detail because in some sense it's the one that comes up most often. But there is this connection.